Okay, good morning, everyone. Let's get started. Let me start again by apologizing for the last week and a half. I'm feeling much better. I've tested negative for the last few days, so I'm all good. Last week and a half was a little bit hazy for me. Hopefully, I was able to walk you through artificial neural networks, evolutionary computation, and we'll finish our lecture today on our third tool of the trade for this class, which is physical simulation. But as usual, before we get back to lecture, a little bit about the assignments. The undergraduates, you're diving into assignment 4. You just finished with sensors, the sense side of the sense, think, act cycle. You're going to switch in assignment 4 to motors, which is good timing. That's what we finished talking about last time in lecture. Your motors are going to be receiving a number, which is going to be interpreted as the desired angle. What the brain of your robot or what your robot wants the motor to rotate the joint to. We'll come back to that in a moment when we finish up physical simulation. For the graduate students, you're tackling assignments 7 and 8. In assignment 7, you're going to be implementing synapses, which is the final connecting link for your sense, think, act cycle. The moment you add synapses, which connect your neurons together, perceptions that are arriving at your robot from the outside world are going to flow through neurons and synapses to your motor neurons. The values arriving at the motor neurons are going to be sent to the joints. The joints are going to apply forces to try and rotate the two links connected by that joint to some desired angle. The moment the robot starts moving, at the next time step in the simulation, that's going to change the sensor values that are arriving at the robot, which is going to change the motor values, and around we go. So for the graduate students, you're closing that cycle in assignment 7. The moment you do, when you move on to assignment 8, you're going to start to build your AI, your optimizer that figures out what the synaptic weights should be, to tune the way in which perception is transformed into action for your robot. As you'll see in assignments 8, 9, and 10, you're implementing a series of increasingly complex optimization methods, exactly like we described in lecture 5 on evolutionary algorithms. When you finish assignment 10, you're going to still have a relatively low-powered evolutionary algorithm. It's relatively simple. It's relatively easy for that evolutionary algorithm to get trapped in local optima, which is, as you remember in the fitness landscape, these are sets of solutions that are pretty good, but there's no step from those pretty good solutions upward towards better and better solutions. One common final project that students tend to tackle in this class is to throw away the relatively low-powered evolutionary algorithm that you have at the end of the 10th assignment and replace it with a much stronger evolutionary algorithm that is less likely to get trapped in local optima. Any questions about the assignments? Okay, just a heads up for the undergraduates in assignment 4. As I mentioned, you're implementing motors. You're going to see a little bit of terminology in here, which we've already covered, and again, we'll come back to in a moment. We're going to distinguish moving forward between position control and velocity control. In position control, we're going to assume that the numbers being sent to the motors are desired positions, which for our purposes, the positions are angles. If we have a piston which is trying to extend or pull together the two parts of the piston, the desired position is the desired length of that piston. In the case of our rotational hinge joints, the position is some desired angle. Yeah? For those of you in your final project that want to add wheels to your robot, you will probably switch to velocity control, where the number arriving at the motor is going to be interpreted not as a position, as some desired angle or some desired extension of a piston. It's going to be interpreted as a desired velocity. The robot wants to spin the wheel at 3 radians per second or 0.2 radians per second. Yeah? Some of you students in the past have created robots with legs. So these are legs that have wheels on the bottom, so basically a rollerblading robot. You can combine wheels and legs together, in which case you're going to combine position and velocity control. So what you'll see in assignment 4 is how you can switch between position and velocity control, which may become useful for those of you that want to play around with wheels in the final project. Yeah. Another pair of concepts you'll come across in assignment 4 is the distinction between open loop control and closed loop control. Open loop control means that the sense, think, act loop is open. It's broken. There isn't a complete loop. When you get to the end of assignment 4, you're going to be sending a sinusoidal pattern to the motors. This is not something that's coming from the robot's sensors. You're going to define a sinusoidal pattern, which is going to be sent to the motors, and the motors are going to interpret that as you want that motor to reach this many degrees, this many degrees, this many degrees, then this many degrees, this many degrees, this many degrees. So the desired position that you're going to be sending to the motors at every time step of your simulation is going to be changing. And the motor is going to be applying torques or forces to try and get the two connected links to reach that desired position. Yeah. So if I send a desired position of 90 degrees, I want to extend my lower arm out to 90 degrees. I might have that desired angle, but then I might ask for a desired angle of minus 80 degrees. I'm going to start flexing my arm in, back and forth, back and forth. Yeah? That's open loop control. We're telling the motor what the desired angle is. It's not coming from the sensors. For the graduate students that are tackling assignment 7 this week, the moment you add the synapses, you're going to be switching from open loop to closed loop control. Once we connect the sensors to the motors with synapses, and we propagate those values through the neural network, like we talked about in lecture 5, then the values that are arriving at the motors, they're still position control. They're still being interpreted by the motors as desired positions, but those values are being dictated by whatever the current sensor values are, multiplied by the synaptic weights. Make sense? Everybody see the difference there? Okay, just wanted to give you an overview of that. You'll see these, you'll get some firsthand experience with these concepts in assignment 4 and 7 respectively this week. Any questions about the assignments? Going once, going twice. Okay, all right, so back to lecture. We are going to finish our segment on tools of the trade today. We've got 2 more slides to go in lecture 6, and then we're going to switch over into a history of the field of evolutionary robotics. We already did the history of AI, which depending on how you count, you can go back several centuries, as we already did. History of evolutionary robotics, this very specific area of robotics, much more recent. So we're going to go all the way back to the mid-90s in lecture 7 in a few minutes. Yeah, okay. Okay, so I think this is where we left off last time. As promised, we were talking about position control here, and we went through this cartoon example where we're assuming in this example that the front leg has been attached to the torso, and at this particular point in time, we are sending to this particular motor a desired position or a desired angle of 60 degrees. Yeah? So that's the value. How do we get from that desired position to forces that are being applied to the links? Remember, the physics engine needs to know the forces that are acting on links to know how to update the simulation. The way you're going to do this in your code is to query the physics engine to get the actual angle of the joint at that particular time step. In this cartoon example here, the current angle is 0. We're going to take the difference between the current angle and where we want the links to be. take that difference, and we send that back into the physics engine, and the physics engine takes it from this point. We tell it that there's a difference. We tell the physics engine that there's a difference between what the current angles are between the two connected links and what we want them to be, and the physics engine will work out the force for us. This last step is something that we're going to just let the physics engine do for us. Yeah? Okay, that's where we left things last time. So we saw sense, we saw act. In sense, we're querying various aspects of the physics engine to get numbers that we want and plugging those into the sensors of the robot. We're doing this in reverse for action. We're computing what we want the robot to do and then sending that to the physics engine to make it happen. And as I just mentioned, for the graduate students, you're closing this sense, think, act loop in assignment 7. Let's see how this actually works. This particular slide is probably the most important slide in the whole course because this is where we bring everything together. Yeah? So continuing my cartoon example here, we've got our two-legged robot. We're going to assume that it has 2 touch sensors, one in the back leg, one in the front leg. We're just thinking about this single motorized joint at the front here. There's a second motorized joint back here, but just to keep things simple in this cartoon, we're going to ignore it. We have a very, very simple neural network controller for our robot. We've got 2 input neurons here, which are going to receive at every time step in the simulator the values from the 2 touch sensors. Our 2 input neurons are connected by synapses to 1 output neuron. That 1 output neuron, whatever value is arriving at that output neuron at every time step, we're sending that to the physics engine, and the physics engine is going to transform that number into forces that it's going to apply to the 2 links that are connected by that joint. Yeah? See how everything connects together? Okay, let's imagine at this particular time step in the simulator, both of the 2 legs are in contact with the ground, so both touch sensors are firing. They're both set to 1. So we copy those 2 touch sensor values into the input neurons. So at this time step in the simulator, we are setting the values of the 2 input neurons to 1. And in this cartoon example here, let's imagine that we take this value, multiply it by this synaptic weight, take this value, multiply it by this synaptic weight, add those 2 numbers together, and we get this raw value of 60 arriving in the output neuron. If you remember back to our discussion about artificial neural networks, we sometimes apply an activation function to a neuron that'll squash the value to within some desired range. Again, just to keep this cartoon example simple, there's no activation function. We just have 2 synaptic weights in this case. I haven't told you what those synaptic weights are. Assume whatever these weights are, they cause a value of 60 to arrive here when the 2 input neurons are set to 1. Imagine, so the value arriving at the motor neuron here is 60. And remember that that value is being interpreted as a desired position. We introduced this convention last time that extension, meaning things that rotate parts of the body out or away from the body, we're going to assume those are positive numbers. And flexion are negative numbers, which are forces that are going to pull or rotate parts of the body inward toward the body. Yeah? You can set up your robot in different ways, but let's try and make sure that we all do things in the same way. So a positive value is going to be extend. You want the parts to rotate outward away from the body. Negative numbers flex inward toward the body. Extension, flexion. Yeah? Okay, so we have a value of 60, which is the current angle is 0. We want the position or the angle of that joint to be 60. So the physics engine is going to apply forces to these 2 connected links, the torso and the upper leg. In this example here, at the next time step in the simulation, those forces applied by the physics engine have started to change. The position and 3D orientation of the lower leg, of the leg, but in this cartoon here, the torso hasn't moved very much. Why not? If we have two links that are attached by a joint, and we have a motor attached, that motorized joint is going to apply forces to both objects to try and open, in this case, open them up, have them rotate so that they have a wider angle between them. So one or both of those objects could start moving in response to that force. But in this case, only the leg has started moving, not the torso. Why?
Is it because we're not allowing the torso to move relative to the rear leg?
We haven't actually said anything about the joint that's attached the torso to the rear leg. We could complicate this cartoon and add a second motor neuron and think through the forces that are acting there. Let's just assume there's no forces going to the joint here. It's just the torso attached to the back leg.
Are forces calculated first for the main link and then for the other one?
It's a good question. So what order are forces calculated? For all intents and purposes, assume it's all parallel. So the force of gravity is acting on all three of these links, pulling them down. And now we have an additional set of forces that's also acting on these pairs of objects. It's not really about the order.
Does the torso have more mass?
It could have more mass. It's drawn in this cartoon as it's bigger. It's attached to some other back leg, which is in contact with the ground. So there's basically more mass back here than there is in the front. Yeah, so that's part of it, right? Remember, F equals ma. So the physics engine is calculating the forces that are acting on these objects and then using F equals ma to figure out how these parts move, and mass is definitely part of it. Yeah. Okay, so it's trying to, the physics engine is trying to apply a force to pull these, or to rotate these two pieces away from one another in a particular way, but based on other things that are going on in the physics engine, one or both of the parts, or in some cases, neither of the parts will actually move. In this cartoon example here, this part has less mass. It has a little bit of friction with the ground, so it also takes a little bit for this thing to get going. We're simplifying a lot of things in this cartoon. Let's assume that this leg starts to move. It starts to rotate a small angle away from the body. The moment it does, at this next time step, obviously the leg has come off the ground, so the touch sensor in that leg stops firing. So at this next time step, when we update the two input neurons, they now have a different value, right? This is the magic of embodied cognition. The moment the robot acts, there is a sensory repercussion to its action, right? The moment I act, there is a sensory repercussion to my action. It doesn't feel like you're acting very much right now, but your eyes are actually saccading or jumping around from me to the slide, to the desk in front of you. You are acting and receiving sensory repercussions of your actions. And your brain is actually making predictions about what those sensory repercussions should be. We'll come back to that later in the course. Yeah? Okay, so in this cartoon example here, the sensor values change. The synapse weights have not changed. So one of the things I want you to internalize as you're working on these assignments is you have multiple time scales that are occurring in your experiment. You have the very slow time scale of robots evolving over time from one simulation to the next. Within an individual simulation, you have a fast time scale from one time step in the simulator to the next. Some things change and some things don't change. From one time step to the next in the simulator, two things that do change are the sensor values and the motor values. One thing that does not change from one time step to the next in the simulator are the synaptic weights. We're going to assume that they stay the same. The synaptic weights change over the slower evolutionary time scale. Your evolutionary algorithm is going to try and find good synaptic weights for your robot so that your robot does whatever you want it to do. So far, so good? Questions, comments? Anything I can clarify? Okay, so continuing our cartoon example here, back touch sensor is in contact with the ground, second touch sensor is not, so it's firing 0. We're assuming that the synaptic weights have not changed. Now, as we multiply this value by this synaptic weight plus this sensor value by this synaptic weight, add those two values together, now we have a value of minus 90. So the moment the leg has left the ground at this time step, now the motor is commanding the joint to flex inward to minus 90 degrees. The motor is now commanding these two links to rotate such that this link rotates up and tucks right up underneath the belly of the robot. This is minus 90 here. Plus 60, 0, minus 90. So far, so good? So if this is time step t, and this is time step t plus 1, what is the robot going to do at time step t plus 2? What is it going to look like? It's going to start rotating inward. The front leg is going to stop extending outward, and it's going to start to flex inward back towards the body because it's a negative number, flexion inward, and it's going to start to rotate back inward and downward. What's going to happen? Let's run this simulation forward in our heads.
The robot might start to fall over.
It might start to fall over. So the front leg has come off the ground, which means it's now starting to tip forward. As the whole robot is tipping forward at this time step, at time step t plus 1, the leg has started to flex back inward. It's reverse direction, and it's coming back down again. So what's going to happen at the next time step? Or maybe the time step after that?
The leg might hit the ground as it's moving backwards.
The leg's going to come into contact with the ground again. What happens inside the neural network of the robot at the time step in which the front leg comes back into contact with the ground?
Will it try to flex back out to 60?
It's going to try and flex back outward to 60 because, again, now both touch sensors are firing. We haven't changed the synaptic weights. So, again, the value of 60 arrives at the motor again, and the leg is going to start to extend back outward again. What's going to happen next? Let's speed up our mental simulation here. We've extended out, flexed back, hit the ground, started to extend back out again. We're going to come back in again, flex, extend, flex, extend, flex, extend. This robot might fall forward on its face, depending, but assuming that we have a small enough time step in the simulator, meaning that there is a very small amount of time that passes in the virtual environment from one time step to the next, we can assume that the front leg is going to have a high frequency but low amplitude rotation. Yeah? The moment it starts to rotate away, it comes off the ground, so it's going to reverse direction, hit the ground, back and forth, and you'll get the front leg twitching forward and back, and it might actually end up pulling the whole robot forward. Yeah? Where is the sinusoidal pattern in here? Where is the frequency defined? Where is the amplitude defined? It's not, right? Through the robot's interaction with its environment, and based on how we've put this robot together, a particular interaction is going to arise, which is that the front leg is going to oscillate back and forth. We can't look inside the brain of this robot and say, there it is. There's the sinusoidal pattern. There's the frequency. There's the amplitude. It's not there. It's not inside the brain of the robot. It's an emergent result of the brain and the body, which is the main message of embodied cognition. Thinking about thinking is misleading. When we think about the kinds of behaviors we are capable of, or when you look at animals acting in the real world, they do certain things, we often come to the assumption that there is some circuit in the brain that is doing all of the behavior. Yeah? It's much harder to think about behavior in this way as something that sort of arises between the interaction of the animal, or in our case, the machine, and its environment. but this is it. This is the way most behaviors arise. So it's good news and bad news for us as roboticists. If we could just program the amplitude and frequency of the leg into the brain, that'd be a few lines of code. We could program it in and off we go. Not so easy to figure out how to design the robot. What should the length of the leg be? What should the mass of the robot be? What should the weights of the synapses be so that we get, for example, some desired oscillation? Maybe we want the front leg to rotate forward and back at about 1 hertz, 1 cycle per second, for example. Not so easy to see how to program the robot to do it. Yeah? Okay, as promised, this is probably the most important slide in the course because it ties together all the tools of the trade, all the nuts and bolts of what you're programming. But it's also a concrete example of this more abstract idea, which is going to undergird pretty much everything we talk about in this class, which is embodied cognition. Mother Nature has spent billions of years sculpting the bodies and brains of animals so that when they interact with their environment, they feed, they flee, they reproduce, they do all the things that we need to do to survive and thrive on this planet. Yeah? Okay. What are the 2 synaptic weights?
Negative 90 and 150.
Negative 90 and 150, right? So if we look at this simpler example where there's only 1 touch sensor firing, 1 times minus 90 is minus 90, 0 times anything else is 0, so we get minus 90. We know what that weight should be. The weights don't change. We want in this cartoon, or we wanted in this cartoon example, that when both touch sensors are firing, we get a desired angle of 60. The other weight should be 150. For a lot of what you'll see in neural networks, usually the weights are restricted to floating point values between -1 and +1. It doesn't have to be. Okay. Any questions about this before we push on? Any questions about physics engines, evolutionary algorithms, neural networks? Oh, speaking of physics engines, I did want to come back to joint normals. There were a couple questions that came up in office hours about joint normals yesterday. I don't know how articulate I was when I explained them last week. So just very, very quickly, let's go through joint normals one more time. We have an x coordinate, a y coordinate, and the z coordinate is our vertical coordinate in our physics engine. Someone was asking about making a snake robot yesterday. So let's imagine we place a bunch of links in our physics engine to make up the body of the snake. I'm drawing these links as separated from one another, but let's assume that these pieces are all touching. Let's assume that I create link 0 here, link 1 here, link 2 here. I attach a joint here, 0_1, that attaches link 0 to link 1. And in this snake robot, we assume this is link 0 and this is link 1. I want to define the joint normal for this joint so that these 2 links are going to rotate through the horizontal xy plane. What's the joint normal that I need to define to cause these 2 links to rotate horizontally relative to one another?
Like
Z, 0, 0, 1, right? So the joint normal is a 3D vector. By defining that vector, we're indirectly defining the 2D plane, which is normal to that vector. So if I give this particular joint a vertical normal, 0, 0, 1, when the snake starts moving, these 2 parts are going to rotate like this relative to one another. Yeah? Let's say, imagine that I attach link 1 to link 2 with another joint out here, 1_2. And let's see if I can simulate this. I want the whole snake to continue rotating horizontally through the plane. So link 1 and link 2, I also want them to rotate through the horizontal plane. I give this joint the same joint normal, right? So this would define a 3-segment snake that's rotating horizontally on the ground. You can try this if you want. This snake, no matter how the snake moves, is not going to really be able to push itself forward or backward. Why not? What's the problem? The physics engine is all correct, but we've made things really hard and possibly impossible for the evolutionary algorithm. There's probably no combination of synaptic weights that it could figure out to get this snake to move to the right, forward or back. Why? Did you have an idea?
Equal friction on all the pieces?
Absolutely. Remember, one of the forces that can act on links is friction. If they're all rotating horizontally, they're all staying in contact with the ground and they're grinding on the ground. If each of these links has a touch sensor inside of them, those touch sensors are always one. The robot is also kind of blinded. It can't tell when it moves whether there's been a change in its environment. So again, you can play around with this. This is probably not a very good design. This is one of the challenges and one of the fun parts you'll come up against in your final project is you can get everything correct in the physics engine, turn it over to the evolutionary algorithm, and it says, I can't do anything with this. Yeah? There are some desert snakes that do restrict themselves to moving on the horizontal plane because they do fancy things with granular material, with soft sand, but most snakes don't. What's one thing we could change here to make it easier for the evolutionary algorithm to get our snake to move? Any ideas?
Could add another link that can go up and down.
We could add another link that could go up and down. I've run out of space here, so let's just stick with 3 links and let's just change one of the joints. So we're going to keep this one rotating link 0 and 1 horizontally to one another, but we want to change this joint normal so that link 1 and 2 are now going to rotate through the vertical plane, through the YZ plane. Yeah? Or if this is link 1, this is link 2, they're going to rotate through the YZ plane. What's the joint normal we need to define for that to happen?
1, 0, 0.
1, 0, 0, right? So here's X pointing in or out of the board. So if I define this joint normal, these 2 points will rotate through the plane defined by the whiteboard here. Yeah? So now we have one joint rotating horizontally, one rotating vertically, and you'll get a snake that does something like this, which again, you can play around with it. The evolutionary algorithm says this is something I can work with. Yeah? Okay, last question about joint normals and then we'll move on. Let's say I wanted these 2 parts to rotate like this relative to one another, to twist about their respective long axes. What would be the joint normal that would cause that to happen?
Something pointing in the direction of the y-axis, or along the y-axis.
Something pointing along the y-axis. So let's define the joint normal to be x equals 0, y equals 1, z equals 0, which as you mentioned would be a joint normal that's pointing along the y-axis. The 2D plane that is normal to this vector is the xz plane, right? This plane here, which is coming out of the board and into the board, which causes them to rotate about this particular plane. Yeah? Make sense? Okay. Again, for some of you, depending on what robot you make, joint normals may not be that important to you. But for a lot of you, playing around with joint normals, a little bit non-intuitive. It's helpful to do some of these pen and paper examples to make sure you get things right. Question?
Do these apply to like more complicated joints where there's more, like less restrictions on the movement?
Yes, absolutely. So we're working with the hinge joint, which is the simplest possible joint. There is the universal joint, which you can create in the physics engine, which allows this object and this object, or this link and this link, to rotate this way and this way relative to one another. So there's 2 rotations that are allowed. You can set the 2 joint normals for a universal joint to define what those 2 degrees of freedom are. Maybe you want to allow this motion and this motion, or this motion and this motion, or this motion and this motion. Yeah? Make sense? Other questions?
How do you set a joint normal in PyroSim?
Sorry?
How do you set a joint normal in PyroSim?
How do you set a joint normal in PyroSim? I put it's further ahead in the assignments. I put the link to it in the slide deck from last time, joint normals. Where did we talk about joint normals? I missed it. Here we go. It's in Learning Module N, Quadruped, steps 23 through 36. Again, for what you're doing at the moment, you probably don't need them, but if you want to jump ahead and play around with joint normals, that's where to find them. Any other questions? All good? Okay. All right, so as promised, moving on, we are now going to go all the way back to the mid-90s and look at the beginning of this field, evolutionary robotics. This is there were actually two papers that were published in the same year. This often happens in science. There are ideas that are kind of out there in the ether, and more than one group manages to actually nail that idea down and publish on it. In this case, there are two papers published in the same year, so there's sort of two groups that are known as sort of the pioneers of this field. We'll talk about the Italian group first and the English group after. So two groups led by, one of them led by Francesco Mondada and another Italian researcher, just to make things confusing. They were working in Switzerland, and back in 1996, they built this relatively simple robot called the Kepera. It's about the size of a hockey puck. And you can see it's got two wheels, a left wheel and a right wheel. And it's got a couple sensors on it. Where have we seen robots with a left wheel and a right wheel and a couple sensors on it before? The light sensing vehicle by Valentino Breitenberg, which he published in the 80s. So these researchers were inspired by the Breitenberg vehicles, which, remember, in that book from the 80s, they were just hypothetical. They didn't really exist. They built a physical version of basically a Breitenberg vehicle. This is not a light follower or a light hater, just sort of the basic architecture. Two wheels. They built it in a modular fashion, meaning you could snap on sensor modules on the top of this little hockey puck here. In this top right image here, the robot has a little gripper, and it's able to close its little pincer around a sugar cube and lift it onto its back. Should also sound familiar. Yeah? Okay. That robot, in turn, inspired some other robots. What's the one up here in the upper right? It's the Roomba. I think actually this is the one. Yeah, this is the Roomba. That's right. If you've bought anything at Amazon in the last few years, it was probably delivered to a human operator by these robots down here that have two wheels. They drive underneath one of these vertical yellow stacks. They pick it up and they drive this yellow stack over to a human operator that pulls your item off a shelf. Most Amazon warehouses are now almost completely automated or on their way to being automated with robots that are based on this Kepera architecture. Yeah? Okay. All right, that's the current. Let's go back to the 90s. In this very first experiment that was reported in 1996, they did not use the gripper. They took this basic Kepera robot with two wheels, and they put a linear vision module on top. This is not quite a camera, but it's almost there. It sends out some light beams across 36 degrees in front of it, so it can see with a range of about 36 degrees. Humans can see about 175 degrees. Within that 36-degree range in front of itself, at every point in time, the physical robot got back 64 numbers, where a lower number represented darkness and a higher number represented light. So if the robot were approaching the whiteboard, for example, and there was an obstacle or a darker object, it would see a dip in these 64 numbers at the center, assuming it's facing head on. Yeah? So it's not getting a pixel array, it's a linear vision module, right? It's basically seeing in 1D. Okay. They took this Kepler robot and attached it with a tether to a desktop computer, no Wi-Fi or Bluetooth back then. And they performed the very first evolutionary robotics experiment. You'll notice that unlike us, they are not evolving robots in simulation and then transferring them to a physical robot. They're going to do all the evolution directly on a physical robot. Why?
Do they not have like the technology for simulation?
No physics engines at that time. The first physics engine was released to the computer games community back in 2000. So this is 4 years before physics engines were invented. So no physics engines, which means we're going to have to do all the evolution on the physical robot, which means they're going to have to do hundreds of trials with this little hockey puck robot. Good thing it's so small, they could do it all on a tabletop. We have the robot attached by a tether to the computer. The computer is going to do almost all of the computation. It's going to run the evolutionary algorithm. It's going to generate a set of synaptic weights. It's going to take that set of synaptic weights and assign each of those synaptic weights to the synapses in the neural network that controls the robot. The neural network is also going to be simulated on the desktop. So the brain of the robot is also in the computer. The only thing the robot does is receive numbers along these tethers that cause the wheels to turn. And the robot is then going to send back along the tether the results of the sensor values. Yeah? So the robot is going to sense and act, but the computer is going to think. Make sense? Obviously, 90s technology, not possible to run a lot of things on this little tiny mobile machine. We want to do as much as possible on the computer. One other twist at this time, they had this little laser emitting device up above the desk, pointing down onto the desk. And based on the values coming back from the laser return values, they could compute, again on the computer, the X and Y coordinates of the robot on the table and the heading, alpha. What direction was the robot heading? So at every point in time, not in the simulation, in the real world, at every point in time, the desktop was sending motor commands, getting sensor values, and also getting the current position and orientation of the robot. They're going to run this robot around on the top of a table. You can see they can place little objects around the robot or near the robot. What kinds of behaviors could you evolve for this robot? Obviously, legged locomotion is out. There's no legs.
Trying to get away from the start point.
Get away from the start point. So drive as fast as possible. It's going to be a very short experiment. Explore an area. Also going to be a relatively short experiment unless you also evolve the robot to
Avoid the obstacles.
avoid the obstacles. Yeah, okay. You're going to avoid the obstacles by driving away from them as quickly as possible. Still a very short experiment. While not falling off the edge of the table. I guess you could put obstacles around the table as well. Yeah? Okay, so at this time, they had this physical robot. There were these relatively new things called evolutionary algorithms, these relatively new things called neural networks. These researchers were starting to put all these pieces together and say, hey, this is kind of cool. We can evolve this robot to do something on the table. Here's what they actually came up with. They built this little circular race course, as you can see in the bottom left here on the top of the table. They ended up not using this linear vision module. This ended up being too complicated, so they took this off. And they put on 1, 2, 3, 4, 5, 6, 7, 8 proximity sensors. These proximity sensors emit an ultrasonic pulse, and then they measure the amount of time until they hear that pulse. So this is kind of like bats and echolocation. You're going to send out a signal and see the amount of time that elapses from sending out an ultrasonic pulse and hearing its return. And then based on that time, they can infer how much unobstructed space there is between the sensor and something else. Question?
How did they prevent the pulses from interfering with each other?
Great question. So ultrasonic pulses, they obviously interfere with one another, so it's pretty noisy. So it isn't exactly a perfect, there isn't a perfect mapping between the amount of time it takes for a pulse to go out and come back and the amount of unobstructed distance between the sensor and something else. It's a little bit noisy, but as long as they're all kind of pointing out away from one another on a circular perimeter, that interference is reduced a little bit. Still noisy, not perfect, but luckily for us, we don't have to worry about these details. We're going to hope that the evolutionary algorithm can come up with a solution to this problem, despite the fact that there's this noise and this additional complication. Yeah? So 6 of these sensors on the front of the robot, 2 on the back, and you can see there are synapses that connect every proximity sensor to the 2 motors, left motor and right motor. So we've got 8 sensors, 2 motors. So if you think of this as a neural network, we have 8 input neurons, 2 output neurons, and a connection from every input neuron to every output neuron. They're going to take all of those, what is that, 8 times 2, all of those 16 synapses, all of those 16 numbers, and they're going to evolve populations of vectors of length 16. They're going to search over the space of all possible sets of 16 floating point values for the set of 16 floating point values that'll cause this robot to do something they want in this maze, which you could, or this arena, which you can probably guess what it is, which is race around this arena as quickly as possible. Yeah? In this particular experiment, they built in a little bit of intuition on their own before they let the evolutionary algorithm take over, which is they set some of these synapses to be excitatory and some of these synapses to be inhibitory. We introduced this terminology when we talked about neural networks last week. An excitatory connection will take a stronger input signal and produce a stronger output signal. An inhibitory connection is a negative weight. The stronger the input fires, the stronger the presynaptic neuron fires, the more it will inhibit or the more it will push down the value of the postsynaptic neuron, the neuron that's sitting at the head of the synapse. You'll notice, if you look carefully, it might be a little bit hard to see in the back there, that all of the ipsilateral connections, so the connections that stay on the same side of the robot, there's an ipsilateral connection, there's another ipsilateral connection, there's another ipsilateral connection, are all excitatory, and all of the contralateral connections, the synapses that cross the body, again, it's a little difficult to see here, are inhibitory connections. So they're basically setting positive and negatives onto all of these synapses, but the actual positive value or the actual negative value is going to be determined by the evolutionary algorithm.
It looks like that's not the case for the 2 on the bottom. Why? Do you know why that is?
I don't know why. It's either a typo or they did actually set some of these contralateral connections to be excitatory. And if so, I don't know why.
Do they run it in both directions around the maze?
Do they run the robot in both directions around the maze? Hold on to that thought for a moment. So the researchers are setting whether or not the synapses are excitatory or inhibitory, but the actual magnitude of those negative and positive values is going to be discovered by the evolutionary algorithm. Why did the researchers do that? Why didn't they just let the evolutionary algorithm figure out which synapses should be excitatory and inhibitory? which of these should be positive and negative, and also what the magnitudes of these 16 connections should be. They're sort of giving the evolutionary algorithm a hint. They're saying focus on these subsets of 16 floating point values. These should be positive and these should be negative. First of all, why do you think they set the ipsilateral connections to be excitatory and the contralateral to be inhibitory? What is the intuition and where is it coming from? You've actually seen it already in a simpler form.
It's kind of like the Bratenberg vehicle that avoided the light.
It's like the Bratenberg vehicle that avoids the light. If you just think about the contralateral connections for a moment, so it's not light in this case, it's proximity. Yeah. So if these sensors on the left are firing more strongly, that means there is something. That is closer to the robot on the left. Yeah. High sensor values mean high proximity. Something is close. If these sensors on the left are firing more strongly, they are more strongly inhibiting the right-hand motor. They're driving down the angular velocity of the right-hand motor, which causes the robot to do what? All other things being equal. There's something close to the robot on the left, which is causing the right wheel to turn slower. What is the robot going to do?
Turn right.
Turn right, exactly, right? It's going to turn away from whatever's on the left. Yeah, that's the contralateral connection. At the same time, continuing this example, we have something close to the robot on its left, so the left sensors are firing more strongly. The ipsilateral connections are exciting the left motor. They're speeding up the spin of the left motor, which is also helping with this turn to the right. Everybody see that? So they're basically taking the coward, the robot that was afraid of the light, and building it in. But by not setting the magnitudes of these synapses, they're going to let the evolutionary algorithm figure out how much or at what speed to turn away from proximity. If there's nothing in front of the robot, if these sensors are all firing at about more or less the same value, it's not quite clear what the robot should do. They're kind of letting the evolutionary algorithm figure this out. So this is the first of many examples we're going to see of evolutionary robotics experiments where it's not completely automated. The investigators are trying to bias the evolutionary algorithm towards the right kinds of solutions and then letting the evolutionary algorithm fill in the details. So far, so good? Okay. So let's get back to what this robot should actually do. They're going to try and evolve this robot to circle through the maze as fast as possible. As has already been observed, they are not telling the robot whether it should drive around the maze forward or backwards. And it should not hit the wall as it does so. Yeah? Okay, so as we've already mentioned, this robot has a particular neural network architecture, 8 input neurons, 2 output neurons, 16 synapses connecting them together. Well, I erased it already, but this robot is going to be controlled by velocity control. The values that are arriving at the 2 motor neurons, we've got 1, 2, up to 8 proximity sensors. We have 1, 1, 2 motor neurons. We're going to apply an activation function so that the values arriving at the motor neurons are squashed to values between minus 0.5 and plus 0.5. So let's imagine that at a given point in time, the left motor neuron has a value of minus 0.5 and the right wheel has a value of 0.5. The motors are going to apply rotational forces to the wheels. Rotational forces are known as torques. So it's going to apply 2 different rotational forces, 2 different torques that are going to try and cause the left wheel to turn backwards at 0.5 radians per second This motor is going to apply a torque that's going to try and cause the right wheel to turn forward at 0.5 radians per second. Assuming that the wheels actually start to do that, what would the robot do? What would this two-wheeled robot do in that case?
Turn left.
Turn left in what way?
Sitting in place.
Sitting in place, right? It's going to stay where it is and just start turning counterclockwise. Everybody see that? Okay. That's the motors. They're going to take the values arriving at the proximity sensors. Whatever these raw values are, they're also going to squash them to a particular range between 0 and 1. A proximity sensor that's reporting a value of 0, here's our 1, 2 through 8 input neurons. 0 means I don't know if there's anything in front of me. I got no pulse back. I sent out a pulse, I sent out a chirp, I heard nothing back. As far as I know, clear sailing ahead of me. Another proximity sensor that reports a 1 says I'm in contact with something. I sent out a pulse or a chirp, I immediately heard the reflection of the chirp. Any value in between 0 and 1 means the object is further or closer away. Yeah? Higher values mean more proximity. Something is closer. So far, so good? Okay. Okay, let's make our fitness function over here. In this paper, they used phi for fitness function. They thought they were being clever. They set up their fitness function so that whatever this value is, if they take whatever set of 16 values they take, drop it into the robot does something inside a maze. They're going to take those raw values back and compute a fitness function that returns a single number between 0 and 1. 0 is the robot did the worst possible thing, and 1 is the best possible performance, whatever that is. Given what we've said so far, if we do drop a set of 16 synaptic weights into our Kepra here, and whatever this fitness function is, it gives us back a value of 0, what did the robot probably do? There's a couple things it could have done to do maximally poorly.
Could have run into a wall.
It could have run into a wall. It could have gone straight, smashed into a wall, and stayed there. It could have done nothing. Could have just sat there and not moved. It could also...
Could have gone through backwards.
They didn't say there's anything wrong with going backwards. As long as it drove through the maze backwards, that's whatever this fitness function is going to be, it should return a non-zero value. That's okay. Crash into a wall, stay still. What else?
You could drive in small circles or spin around.
Spin in place, make little small circles. Exactly, right? There's an infinite number of bad things it can do, only a few good things that it can do. Okay. Let's practice building a fitness function ourselves. Let's imagine we're going to build it out of the following values. Let's say we're going to run this robot for 10 seconds, for example. And let's imagine we're getting back the speed of the left and right wheel at every 10th of a second. And we're also getting back the values of all 8 proximity sensors at every 10th of a second. So we're going to run the robot for 10 seconds. We're getting these 10 numbers at every 10th of a second. So we have a matrix basically of 10 times 100 numbers. 10 seconds, we're pulling the values at every 10th of a second. Yeah? We're going to combine all of these numbers together into a function that'll give us a 0 when it does these bad things, and give us a higher and higher value when it races around this track faster and faster without hitting the walls. Generally speaking, what would you put into this equation? How would you start constructing this fitness function?
You want to have high speed in either direction, so, well, I guess it's already speed and not velocity. If I was going to say the absolute value of the speed of the left and right wheels.
The absolute speed of the wheels, right? Imagine we just stuck in VL plus VR into this equation, right? So we're looking for positive values of VL and VR. That would evolve a robot. It would evolve a set of synaptic weights that maximize VL and VR, spin both wheels forward as quickly as possible. right? It'll take off and crash into a wall. So it's a good start, but not, it's a fitness function that isn't selecting for what we want. So a better thing might be to take the absolute values of VL and VR, which would select for spinning forward or spinning the wheels back, which is good. That's going to start to evolve a robot that moves. Staying still is no good.
You would put the absolute values around after you sum them?
Do we put the absolute values after we sum VL or VR or before? So the way to figure this out is you sort of think of it. We could take the absolute value of VL plus the absolute value of VR, and then think about behaviors for the robot that would maximize or minimize that function. What you'll probably see very quickly is you can start to imagine examples of perverse instantiation, ways that the robot could behave to maximize that value, but not do what we want it to do. Yeah? So what usually happens in evolutionary robotics and AI in general is you come up with version 1 of your fitness function or your objective function, put it in your robot or your neural network. It easily maximizes your fitness function, does exactly what you didn't want it to do. You go back, build version 2 of the fitness function. It perversely instantiates it again, version 3, version 4. You'll see when you get to the final project. You'll go through several versions of your fitness function. For these researchers, it's not exactly clear what version this is, but you'll be able to see pretty quickly this definitely wasn't version 1. So you'll notice that they multiply 3 different terms together. We're going to assume for our purposes that all of these terms are positive. They also all range between 0 and 1. So they're basically saying, okay, robot, maximize this. But while you're maximizing this, you also have to maximize this. And, oh, by the way, you also have to maximize this. Yeah? By multiplying these 3 terms together, we'll talk about what these terms are actually selecting for in a moment. By multiplying them together, it ensures that evolution doesn't produce a robot behavior that maximizes just one of these terms, but ignores the other ones. It lets the other ones drift down towards 0. Yeah? If we had summed these terms instead, evolution might have focused on one of these terms and figured out sets of synaptic weights that bring that term up towards its maximum, which is going to be 1, and sort of forget about the other 2. Yeah? So you can already see mathematically how the investigators are starting to exert selection pressure on this evolving robot. We're specifying what we want it to do, or actually that we want it to do more than one thing. We want it to do 3 different things simultaneously. Everybody see that? Okay, let's start with term number 1. This is the easiest one, V. We got pretty close to this one already. They're going to sum the absolute value of VL and VR. So the absolutes are placed there because the investigator said, we don't care whether you rotate back, the wheels rotate backwards or forwards. They just should rotate at highest magnitude. Whatever the robot should do, it should always be spinning its wheels. Yeah? Okay. However, that's not going to be sufficient for our purposes, right? Because as we've seen, one perverse instantiation of just V would be spin the left wheel forward and spin the right wheel backwards. So maximizing V alone, one way to do that is for the robot to turn in place. So they added a second term, this one here, 1 minus the square root of delta V. Let's talk about delta V first. Forget about the 1 minus square root for a moment. What is delta V? What would be a high delta V here and what would be a low delta V in terms of the robot's behavior? High delta V would be delta V. The wheels have very different V's. They have very different velocities. Yeah? Let's forget about the square root for a moment. 1 minus delta V? Why 1 minus?
Because you don't want that.
You don't want that. We're going to see lots and lots of fitness functions in this class, and a lot of them are sort of double, triple negative, so you got to sort of think through this. So they're basically saying delta V is bad, so minimize it. We're going to assume that delta V ranges between 0 and 1. If it's something we don't want, a delta V of 1 is the worst possible thing you can have. A delta V of 0 is the best possible thing you can have. Take 1 minus. Anybody see why they added in the square root? This is kind of a detail. Not that important, but you're taking the square root of a value that ranges between 0 and 1.
Like if you think about the square root function between 0 and 1,
Yep.
the biggest changes for like a given step size are going to happen closest to 0.
Are going to happen closest to 0, exactly, right? So if we have delta V on the horizontal axis here that ranges between 0 and 1, and we plot the square root of delta V over here, it's got this shape, yeah? So even a small amount of delta V is going to give a big square root of delta V value. So by adding the square root, they're putting more pressure on delta V. They're saying delta V is bad, but it's actually really bad. Don't even start trying to increase delta V. Yeah? So they're sort of turning up the strength of selection. This is a term from evolutionary biology. They're making it really bad for the robot to exhibit a delta V. Okay, so we're multiplying V. Let's just think about these two terms for a moment. So multiplying these two terms together, what does that select for? Forget the third term for a moment. What kinds of behaviors are now good and what kind of behaviors are now bad?
Move in one direction quickly.
Move in one direction quickly. That could be go forward quick, so big V, small delta V, or big negative V. Move in the back, move backwards, don't turn. But not turning is bad if you're in a circular arena. So they're going to multiply that by this third term here, 1 minus I, where we're going to assume that I is the maximum firing of all of the 8 sensors at any of the time steps. Remember, we're letting the robot run for 10 seconds, and we're polling all the sensors at every 10th of a second. So we've got 800 numbers here, 8 times 100. Out of all those 800 numbers, take the one that's closest to 1, or the one that is 1. What does that represent?
Try not to hit a wall.
Try not to hit a wall, right? Or stay away from things. Yeah. Okay, let's put all of these together. So multiplying these 3 terms together, what does this select for? Or what does this select against? What kinds of behaviors does this select against? What kind of behaviors does this select for? Go fast, turn as little as possible, while also staying away from obstacles. Yeah? Sounds good. I'm curious to know how many iterations they had to go through this experiment to actually get this, right? They're sort of saying, do this, but don't do it in this way, and also don't do it in that way. We're going to see a lot of fitness functions that actually look like that. In theory, in evolutionary robotics, the dream is obviously, we say, go clean up Innovation Hall. We don't care about the details, robot, of how you do it. Go out and do it. In practice, with robots and with young humans, can't get away with that. We've got to give some guideposts. Please go clean up innovation, but don't throw out the chairs and the chalkboards and the walls and the ceiling. Focus on these things. You've got to give a little bit of guidance about what to do and what not to do. Okay. All right, so now they've got everything in place. They ran this experiment where they created a population of length 16 vectors. They took each vector, sent it to the robot, or downloaded it onto the desktop, ran the robot for 10 seconds, got all the sensor values back, computed how well the robot did, picked up the robot, put it back in the same place in the maze, took the next length 16 vector, allowed that robot to run for 10 seconds, recorded everything. The code probably crashed. They had to start it again. Somebody had to come and reset the robot. Someone needed to take a bathroom break. Someone needed to go get a coffee. And then they did the third one, fourth one. They did the 100th one, which took 40 minutes. So they got through one generation of trying out 100, maybe 200 sets of synaptic weights, which gave them this data here at this evolutionary time. Again, I apologize for the quality of this figure. Trust me, this particular robot, among those 100 or 200 behaviors, didn't do a very good job of racing around the maze without hitting the walls. Yeah? They deleted the vectors that did a really poor job of controlling the robot based on this fitness function. They deleted half of those vectors that got lower than average phi. And then they made randomly modified copies of the surviving vectors. For all of those new vectors, they downloaded each one onto the robot for 10 seconds apiece and continued this process for 100 generations, which took 66 hours or a little under 3 days in total to do. Yeah? You can see why you're using a physics engine and not doing this all by hand on a physical robot. Okay, at the end of that process, at the end of these 3 days, they had a robot that had a certain value for phi. We can't really look at the value of phi, which ranges somewhere between 0 and 1, and know how well the robot did. So they made this, again, apologies, very low-res visualization of what the robot did. Each line segment here corresponds to 1/10 of a second during this 10-second period. The center of the line segment represents where the robot was, and the orientation of the line segment represents the heading of the robot at that time. How did the robot do? Pretty good. It got all the way around the maze. Is this the optimal solution? Is this the best the robot could do? Probably not. Why not? There's some immediate clues that tell you this is not optimal.
I think when it's kind of going up and to the right,
Yep.
it looks like it's kind of going, like it fires
Oh.
one motor and then fires the next one.
Yeah, exactly. When it's moving along this leg of the track, you can see it sort of wobbling back and forth. Yeah.
It only really wants to turn when it starts to approach like a far region, and it would be faster to take tight corners.
Absolutely, right? So you can really see it down here. So you'll notice there's a whole bunch of line segments right on top of one another. The robot is basically grinding to a halt and then turning and then taking off again. Yeah? It's not perfect. Evolution, artificial evolution or biological evolution, is a satisficer. Satisficer, not an optimizer. Evolution is not guaranteed to find the optimal solution. Time and time again, it finds things that are pretty good, which is good news for us. We are clearly not optimal creatures, however you want to define that. This is also not an optimal creature, but not bad. Okay, we got 2 minutes left. What you're seeing in the bottom left picture here is, again, evolutionary time here. And they've broken up the behavior of the best robot. So remember, at every point in time here in the evolutionary algorithm, we have 100 or 200 robots. I don't remember what it is, doesn't matter. One of them is getting the highest value of phi. They took that value and broke out or computed the values of those 3 terms that are being multiplied before, and they drew them. The solid line is uppercase V. This is the velocity of the best robot in the population at any point in evolutionary time. The dashed line up here is how well the best robot is doing at avoiding the walls. And the dotted line here is showing how well the robot is doing at minimizing delta V. How did evolution proceed in this case? How did evolution balance all of these 3 desiderata, these 3 things that we wanted the robot to do? What happened during evolutionary time?
They didn't think that minimizing delta V was that important.
It didn't, yeah, you can see minimizing delta V didn't drop to 0. So there was Definitely differences in the speeds of the two wheels. What else happened during evolution here? Tell me about uppercase V. What happened over evolutionary time?
Is that the dark line?
The dark line, yeah, the solid line here is uppercase V.
Got faster.
The wheels got faster. Doesn't necessarily mean the robot got faster, right? Just that the wheels are spinning faster. At the beginning, the wheels were barely turning at all. The wheels got faster and faster. As the wheels got faster and faster, delta V started around here and dropped a little bit. So it's trying to reconcile, obviously, going fast. But delta V can't go to 0. Why not? It can't zero out the 1 minus square root of delta V altogether. Why not?
Because it has to turn.
It has to turn, right? So evolution is trying to balance out a lot of competing traits, right? Making one trait better necessarily makes the other one worse, and vice versa. Yeah? It's doing the best it can. Okay, I think this is a good place to pause for today. You have a quiz due tonight. Undergrads, you're working on A4. Grads, you're working on 7 and 8. Have a good rest of your day. I'll see you on Thursday.